Hi there, welcome to the video on section 3.2. We're going to be learning a couple new derivative shortcut rules, and then we're just going to be practicing finding a bunch of derivatives. I'll give you a few tips, but right now we're just practicing using various shortcut rules so that we don't have to use the difference quotient for all of our derivative calculations. So what are these two new formulas, these two new shortcut rules? One of them is called the product rule. The word product in mathematics means multiplication. So when you multiply two functions together, f times g, to find the derivative, right, to find dy dx, you're going to use this formula right here. Again, not too hard to prove. Nice little demonstration in your book. So we can go together, but I'm not going to use this video time to demonstrate all these formulas since they're well-known proofs of why these are correct. So this is the derivative of the product of two functions. If you have two functions that are being divided, then there's a different rule. So two functions being divided, called the quotient rule, because it's the quotient of two functions. You get this formula right here. It's the derivative of the top function f times the bottom function g minus the reverse of that, which would be the derivative of the bottom function g times the top function f. And all that is being divided by the bottom function squared, g squared. So a bit of work here to do the quotient rule, but that's a shortcut. You know, if you don't want to use a shortcut, that's fine. You can go back to the difference quotient. I think the quotient rule, as much as it may be kind of a lot of steps, is a lot less than the difference quotient. So use it when you can, is my advice. All right, so I have three examples here just to start off that are already typed out. So the first example, I guess I'll just leave these like this and shrink my screen a little bit. Okay, so the first example, I have my function as example A, y equals x squared plus 3x plus 1. And this one, it has like different things, x squared, 3x, and 1, but they're being added together. So the adding rule is not the same as the multiplying or dividing rule. The adding rule we did in 3.1. And the adding or subtracting is very nice because you can just differentiate them piece by piece. So the derivative of x squared plus 3x plus 1, we can differentiate x squared, we can differentiate 3x, and we can differentiate 1, each of them separately. And then what do we use? We can use the power rule. So once again, from section 3.1, make sure to write down those formulas or commit them to memory. The derivative of x squared is 2x to the first power. We don't have to write the power of 1 because anything raised to the power of 1 is just itself. So we can just write 2x. The derivative of 3x is 3 times x to the 0, or just 3. And the derivative of any constant ends up being equal to 0 as well. So our derivative, once we simplify it, is 2x plus 3. All right, second example here that I've already written out is a multiplication of two functions. It's 3 to the x times x to the fifth. When you're multiplying two functions together, that means you'll need to use the multiplication rule, or commonly referred to as the product rule. And so we would do the derivative of the first function, that's the derivative of the 3x part, times the second function, x to the fifth, and then reverse that, derivative of the second function times the first function. And we're referring back to our 3.1 shortcut rules for derivatives. The derivative of 3 to the x is 3 to the x ln 3. That's, again, just from section 3.1 derivative shortcut rules. The derivative of x to the fifth is 5. Oh, the derivative of the first guy times the second one. So it's the derivative of 3 to the x times x to the fifth. So the derivative of 3 to the x is this part, and then times x to the fifth. So we're just multiplying by the second function. And then over here, we have to do the derivative of x to the fifth, which is this guy right here. Oops, that was supposed to be a different color. This guy right here times the second part, which is here. So that's what our answer is. There's some simplification that you can do. You can factor out an x to the fourth, and that actually may be useful. So we are going to ask you to simplify some of these. Don't go overboard in simplifying. You know, we want you to focus on the calculus, not on the algebra. So if you want to simplify this, you could factor out an x to the fourth. And then the first part, we'd have, 3 to the x is also common. So you could factor out x to the fourth, and we could factor out a 3 to the x. My pen stopped working. All right, hold on a sec. Okay, so x to the fourth and 3 to the x are both common. So in the first term here, if I take out the x to the fourth and I take out the 3 to the x or divide by those guys, I'm left with an ln3 and I'm left with an x. And those are being multiplied. And then the second part is separated by a plus sign and I'm left with a 5. And that's it, because the x to the fourth got factored out and the 3 to the x got factored out. So you could simplify this. I'm not sure if this is like if you took a vote, whether a majority of people say this is simpler than the original one. But some people really like simplifying, and this is how you would do it. For that, you just factor out common things. All right, and then my last pre-written out example is the division of two functions. So this is example C. I'm going to just refer back to this shortcut rule. This is the shortcut rule. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom function squared. Because I need to zoom in on this. I know some people use like a phone or a small screen. So I'm going to zoom in so that people can see a little bit more what's going on here. So this is the function. It's a division of two things. So we're going to use the quotient rule. And I'll rewrite it here just so you reference. The derivative of the quotient rule, you do the derivative of the top part, which I call f, times the bottom function, minus the derivative of the bottom function, times the top function, and then that's a fraction that's over the bottom function squared rooted. And so I have here the derivative of the top times the bottom. Notice that instead of writing square root of x, I'm writing x to the 1/2 because there's no formula for the derivative of the square root, but there is a formula for the derivative of x to a number. So we're writing square root of x as x to the 1/2. So that's the derivative of the top times just the bottom, no derivative of the bottom there. And then we have the derivative of the bottom and then times the top. And then you have on the bottom, the bottom function squared. So we'll need to differentiate this. This is the derivative of x squared plus 3, which is 2x plus 0. So derivative of x squared is 2x, derivative of 3 is 0. I just leave alone the second part, x to the 1/2 minus x. I differentiate this thing right here. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of minus x is minus 1, and then I multiply by x squared plus 3. So I'm just following this algorithm, basically, for finding the derivative of this very complicated function using our various shortcut rules. So just kind of doing a minimal cleanup, you get something looking like this. Now, we should combine things together. Like, we don't need a plus 0 for the 2x. That is something in which, like, we should just write as 2x, right? And we can multiply 2x times x to the 1/2. You can multiply two powers that have the same base by just adding the exponents. So if I have x to the 1 and x to the 1/2, 1 plus 1/2 is 3/2. So that's where I got 2x to the 3/2. Multiplying 2x to the 1 times minus x is minus 2x squared. So I'm just kind of doing some minimal combining together, powers that have the same base, getting rid of zeros and ones as appropriate. So do some minimal cleanup here is what we're looking for. And you end up with this guy right here. Now, there's definitely more simplification you could do. For example, I guess there is more simplification I definitely should do because there's things that are alike. There's a minus 2x squared and there's a plus 2x squared. And those are easy to combine together because they are powers that have the same base and they have the same exponent, so we can add or subtract them together. Is there anything else that can be combined? Oh, yes, here we go. We have 2x to the 3/2 and we have minus 1x to the 3/2. These are two powers, share the same base, share the same exponent, so I can add or subtract them together. This is added or subtracted, but it has a different exponent, so I cannot combine that together unless it was multiplication or division. It's addition, so I can't do it. And 3 is just a number. So let me combine together these red guys. 2 things minus 1/2 things is 1.5 or 3/2 of those things. In this case, x to the 3/2 is the thing. So I have 3/2 times x to 3/2. The minus 2x squared and the plus x squared ends up being just minus 1x squared. And then I do have these other things that I could not actually simplify. The minus 3 halves x to the minus 1 half, and the plus 3. It should be a minus 3. No, it is a plus 3. That is a plus 3. Okay, and then the bottom thing we have here is this bottom function squared, square root of x minus x squared. So that actually looks pretty good to me. Again, there is more simplification that can be done. You, as a student, may be tempted to multiply out the denominator because you can see that there is a distributive property you could do. Square root of x minus x, you could just multiply it all out and see if it simplifies. In my experience doing mathematics, it almost never helps to multiply at the bottom. It does help to multiply at the top. A lot of things will combine in the numerators of these things, but almost never will things really end up combining. Sometimes, it's a 1%er, but it's a lot of work for almost always no payoff. So we typically leave it like this, combine as much as we can in a simple way, combine together things that are alike or powers that have the same base, and then say that's good enough. So for me, that is good enough for example C. Quotient rule with a couple of complicated functions. You can see there's a lot of algebra, a lot of steps. So that's what you're going to be doing in 3.2, doing a lot of algebra, a lot of steps, keeping track of all the different rules and formulas, trying to see if you can not make any mistakes with the minus signs or the fractions or whatever, and see if you can get the correct derivative at the end. So that's our goal. We're going to be doing more of this in 3.3 and 3.4, but right now we're going to be focusing on 3.2, which is all the stuff we did in 3.1, plus the product rule and the quotient rule. Okay, so I'll give you a couple tips, and then we're just going to do a whole bunch of examples, and that'll be it for this video. All right, so for the tips, well, that is very small. For the tips here, just be a little careful with the product and quotient, the multiplication and division rules. The rules are meant for the multiplication of two functions that move, right? They're actually like, x's or things that have a variable in them. If you have this thing you're trying to differentiate 4 times the square root of x, a lot of people focus on the multiplication symbol and say, oh, that's a multiplication of two things. That is a multiplication of a number times a function. And we have a constant multiple rule, which is way, way easier than the product rule. So if you're trying to find the derivative of, if you're trying to find the derivative of this function, 4 times square root of x, then the constant multiple rule says if you have a constant that you're being multiplied, it just does not affect the derivative in any way. So we just differentiate the square root of x part and multiply our answer by 4. And by the way, if you need another reminder, there's no rule for the square root of x, but we just write this as x to the 1/2. Right, so then we differentiate that. In a similar way, x squared over 3 is not the division of two functions. That's a function divided by a constant. So if we were going to differentiate this particular thing, this x cubed over 3, or x squared over 3 is I think what the function actually is. That is clear on my screen. The over 3 is just divided by 3. It's just a number. So we can write this as 1/3, that's the divided by 3 part, times the derivative of x squared. So no quotient rule for this one, because it's just 1/3 times the derivative of x squared, which we can do using the normal power rule. And then my last tip is that I do have a bunch of formula sheets on Canvas. So if you go to our Canvas page, and you look up, this is my version. This is like the teacher version of Canvas. So it may not look exactly like yours, but it has the same banner. And you'll see it has under the instructional videos where you found this particular video, you'll see, or above it, you'll see formula sheets, handouts, etc. So if I follow this link, I get to this next tab. So this is the formulas page. And I have a review sheet for exponent and log formulas. I have a review sheet for trig formulas, and I have a derivative formula sheet where it shows you the shortcut rules that you learn for derivatives in Calc 1 class, and it's like this. I just pre-open these because sometimes it takes a while to load them in, depending on whatever the electrons and how fast they go, I guess. So this is the derivative formula sheet. And I try to list them, in the order that we sort of do them more often. So we've done 1, 2, 3, and 4 so far. So we have done the first 4 derivative formulas in section 3.1. And then if you scroll down, we have some generic rules here. We've also done the first 4 of these: multiplication by a constant, adding or subtracting, called the sum rule, the product rule, multiplying 2 functions, and the quotient rule is dividing 2 functions. So we've done the first 4 of these derivative rules, as well as the first 4 of these derivative shortcut rules, or derivative formulas, as they're usually referred to. And all the ones we're doing in Calc 1 are listed here, so you can just have this reference sheet. Of course, there are lots of reference sheets online if you'd prefer to use one of those instead. So that's my second tip right there. All right, so for the remainder of this video, I'm just going to be demonstrating the derivatives of many functions using the shortcut rules. And as always, I invite you to pause the video and try these instead of just watching me do them. Try them yourself. And then you can come back and see how your solution compares to mine. If you've got a similar answer, if you simplified it in a different way that I did, etc., or if you got stuck, you'll know where you got stuck and what to do, how to proceed next. So it kind of is a good experience if you actively engage in solving these problems, as opposed to be passively viewing how someone else solved those problems. Okay, so I'm going to do the first one here. The function is y equals 10x to the fourth minus x squared plus 2x minus 7. And in every single one of these problems that we're doing on the next few pages, we're going to be looking for the derivative dy dx. Okay, so for this first function, it's the sum or difference, same thing, of 3 or 4 different functions being added together. So to find the derivative, because they're being added or subtracted, I just find the derivative of each part. 10x to the fourth is a power rule, so it's going to be 10 times 4x cubed. The derivative of x squared is going to be minus 2x to the 1. The derivative of 2x is going to be 2x to the 0. And the derivative of 7 is 0. And then we should simplify this just a little bit. 10 times 4 is 40. And then 2x to the 1, we don't need a 1 exponent because it's a default exponent of 1. X to the 0 is 1, so this is just 2. 2 times 1 is equal to 2. And I don't need to write the minus 0. So this is my answer for the derivative of 10x to the fourth minus x squared plus 2x minus 7. You don't have to do all the steps I'm showing. Like, a lot of students will go directly from this to this. They don't do the intermediate step of 10 times 4x to the third. They just write 40. Don't feel like you have to show those steps when you're doing problems. You could just write 40. It's fine. I know where that came from. I know you multiply 10 by 4 in your head. Don't worry about that. But I do want to see, like, the fact that you're doing like 3 different parts. That would be nice to see, so that I understand that you're applying that rule. All right, example B. I have a power rule times an exponential. The constant in front, 6, does nothing. So I'm going to do 6 times the derivative of 5x to the fifth, which is 5x to the fourth. Again, feel free to combine those together to be 30. And the derivative of 6 to the x, well, that's an exponential. So the derivative of an exponential is the same exponential times the natural log of the base. Like I said, you could just write this as 30x to the fourth minus 6 to the x ln 6. All right, example 3, we have square root of x, 3 to the x. two different objects put together with no sign in between them. The default is multiplication. So this is supposed to be interpreted as square root of x times 3 to the x. And because we are multiplying two different functions together, we're going to use the multiplication rule or the product rule. So I'm going to differentiate this first function. I'll circle the first function in blue here. I'll circle the second function here in red. And the product rule, the multiplication rule, I do the derivative of the first times the second plus the derivative of the second times the first. You may want to understand that I don't really differentiate square root of x, right? Because there's no really rule for square roots. You have to write or think of this as x to the 1/2, right? So kind of remember that fractions are good, roots and radicals, not so much. Okay, so what is my derivative for this one? Let's just do this in black. So I differentiate the first function multiplied by the second function plus the derivative of the second function times the first function. So that's classic power rule right there. Excuse me, classic product rule right there. And then I do have some things which are common. I have a 3 to the x, which is common. So you could factor that out. And the first part, I have a 1/2 x to the minus 1/2. And the second part, I have an ln 3 times x to the 1/2. And that's pretty good. That's a good simplification there. I guess you didn't have to do that to factor 3 to the x out, so you could have left it as the one before, but a lot of people like factoring out that common 3 to the x. I will show you something else, just in case you are interested. There are two x to a power, like polynomials with the base x. There's x to this number, and this supposed to be a different color. There's x to this number. Color, please. Okay, there we go. X to this number and x to this number. Right? There are two powers that have the same base. And you can factor two powers that have the same base. For example, if I had x to the 4th minus or plus x to the 3rd, you could see that you could factor out x to the 3rd. You could factor out the smaller of the two powers, right? The two exponents, which are smaller. You could say this is x cubed times x plus 1, right? Because you're factoring out the common x cubed. It's always the smaller number, which is going to be the common one. So what's common here? Well, you have these powers, they have the same base. So the smaller number is the one that's common that we factor out. So you can actually factor out, well, we already factored out 3 to the x, but we can also factor out the x to the minus 1/2. So we factor x to the minus 1/2 out of the first guy, you're left with just 1/2. And we need to factor x to the minus 1/2 out of this guy. And if you think about it, you're just subtracting exponents, right? If you think of my little example up here, you just do 4 minus 3 and you get 1, right? So you're just factoring out the smaller one, which means you're subtracting or dividing it off. X to the 1/2 divided by x to the minus 1/2. I subtract the exponents. 1/2 minus 1/2 is x to the 1. Like that. In fact, we don't even have to write the 1, right? Because if you don't write the exponent, it's assumed to be 1. So this is even more advanced simplification. You do not need to do this to get full credit. There are some problems in the future where you will need to do this kind of factoring. So I thought I'd just do an opportunity to show it to you now in case you want to practice it a little bit, so that when you get to that future, sort of more complicated problems, you're like, oh yeah, no problem. I can factor out the smaller of those two powers. In this case, you'd factor out the x to the minus 1/2. All right, this last little demo problem I'll do on this page is example D. And for this one right here, it is x cubed minus 8 squared. So what do we do here? Well, you can see this as the product of two functions. You can write this as x cubed minus 8 times x cubed minus 8. and that is the multiplication of two functions. They're the same function, but you're still multiplying two functions together. So I could use the product rule and multiply the derivative of the first times the second plus the derivative of the second times the first, sort of like we did in this problem, just two different versions of f and g, and we can just multiply those out. So you could use the product rule to differentiate this guy if you just write it as a product. Alternatively, you could use some algebra because we know how to simplify the multiplication of parentheses. It's called the distributive property. Some people call it foiling, but I could just multiply this out, x cubed times x cubed, and then I get minus 16x cubed, and then minus 8 times minus 8 is plus 64. And now I'm not multiplying any functions together, so I could use the sum rule because I'm adding or subtracting functions together. You'll get the same answer either way, and it's kind of your choice which one you want to do. I'm just kind of showing you some options. I will do the sum rule because at this point it's much easier than the product rule. Derivative of x to the sixth. The derivative 16 doesn't do anything, so it stays right there because it's a constant being multiplied. The derivative x cubed. Come on, pen. There we go. And the derivative of 64, you may remember that the derivative of any constant is going to be 0. Another way of thinking that is that a constant function, y equals 64, that function is just a horizontal line. It's at a height of 64 in this case. But the slope of a horizontal line is 0. The derivative measures slope, so it's going to be 0, right? I mean, you're just measuring the slope, and we know the slope is 0. Okay, and we'll clean this up just a little bit by combining together the 16 and the 3. 16 times 3 is 48. You could factor this, right? Because there's an x squared that's common if you really want to. You could factor out a 6 if you really want to, because 6 is common. Like this. I don't know what the best answer is. You could argue about it. I'll take any of them, right? It's just, again, how much work do you want to put into simplifying other than the basic just combine like together? Is that really up to you, right? I just want you to be able to do the calculus and the algebra, all this kind of simplification is not really our main focus at this point. All right, so for the rest of this video, I am going to, again, invite you to pause and try these problems. So I have e, which is y equals e to the x over 2. This is not a division of two functions. Remember, 2 is a constant. We have f, which is a fraction. Again, not the division of two functions because 3 is a constant. G, you actually have a function on the top. You have an x, so things are moving on the top. You have a function on the bottom. You have an x, so things are moving on the bottom. G is definitely a quotient rule problem. There are some algebra tricks you can do to try to avoid the quotient rule, but let's practice the quotient rule on part G because it is a function divided by a function. Likewise, in H, it's a function divided by a function. These constants are being added on. There's no adding constant rule. It's a constant multiplication rule, so we can't use any rules but just the sum or difference rule to differentiate them when we get the chance to. Then we have I, which is x to the third over the q root of x. Remember, the q root of x you need to write as a fractional exponent. This is the quotient of two functions, so you can use the quotient rule, the division rule for functions. However, if you do some algebra, just a small bit of algebra, you can actually avoid this division quotient rule because you're putting a little bit of work into simplifying it before you actually find the derivative. So on this page, there are these 5 examples, and I am going to invite you to pause the video and try these 5 examples. Try to see if you can find the derivative of each of them, and then unpause the video, and I will have the solution to all 5 of them and give a very brief overview of my strategy. But I'm not going to play out every single step for these. If you want to see, like, how did I get from one step to the other, just reach out and I will definitely fill in whatever parts are not clear about how to find the derivative of each of these functions. All right, so pause and give them a try. All right, so welcome back. I've written out my solutions to these 5 problems. Hopefully you have done as well. So in E, I wrote this as a constant times a function e to the x. E to the x is very interesting. Its derivative is exactly the same as the original function, which means the slope at every point is the same as the y value at every point. It's what makes E very interesting as a number, or one of the things that makes E very interesting as a number. So it ends up being the exact same function, e to the x over 2, when I differentiate it. Very interesting. For f, I wrote this as 3 times x to the negative fourth, because a fraction can be written as a negative exponent. And then I just used the power rule and simplified, and I got negative 12x to the negative fifth. Or if you want to rewrite it as a fraction, you would have negative 12 on the top and x to the positive 5 on the bottom. For g, I did use the product rule, derivative of the first times the second, minus derivative of the second times the first over the second function, the bottom function squared. And did a little simplification and got to this point right here. And then went down a little rabbit hole of, I could simplify things. I could factor out 2. I can factor out an x squared, which is smaller than the 2x things. I can factor out an e to the x. So I got something like this. This is stuff factored out. And then once you factor things out, you'll notice that there's something on the top and something on the bottom that are both powers with the same base. So I can subtract the exponents or cancel out, divide out. I have 1x on the top and 2x's on the bottom, which means I have 1x left over on the bottom. So if you do want to go down the rabbit hole of simplification, you might get something looking like that for G. Okay, for letter H, again, it's a quotient rule problem. It's getting pretty complicated. The top and bottom are getting pretty complicated functions. So I wanted to show you a way of doing this where you don't have to keep track of everything in your head. A lot of times, if you try to keep too many things moving at once, you start forgetting little bits and pieces. So the way you can do it is you could just say, make a plan. I'm going to differentiate the top times the bottom minus the differential of the bottom, excuse me, times the top over the bottom squared, right? So you don't actually have to do all the derivatives in one step. You could say, I'm going to differentiate this, multiply by x to the 7 plus 8. Then I'm going to differentiate the other one and multiply by x to the 5th plus 6. And then on the next step, actually do the derivative. So the derivative of x to the 5th plus 6 is just 5x to the 4th, and then I have multiplied by that bottom function. The derivative of x to the 7th is just 7x to the 6th, and I multiply by that top function, and then I get over the bottom squared. And then if you want to do some simplification, you might notice that, well, in these guys right here, there's an x to the 4th, which is common, so I factor that out, and I combine together the things inside. And that's about it. So I'm not sure how much you want to simplify, but I did a couple of examples of simplifying for those people who want to explore that. And lastly, example I, this was the function x to the third over the cube root of x. And as you might remember, we need to write that cube root of x as x to the 1/3 exponent. And if you did the quotient rule, you did fine. You can get the right answer using the quotient rule. The right answer is down here. But please check this out. You have 2 powers. They have the exact same base x. And so you can just subtract the exponents, right? When you ever have 2 powers are being divided, they have the same base. You can subtract the exponents. For those who want a little review on their fractions, 3 minus a third is equal to 8/3, right? 9/3 minus 1/3 is 8/3. So this function simplifies just to be x to the 8/3. And differentiating x to the 8/3 is as simple as the power rule. 8/3 comes in front, multiplied by x, one smaller exponent, then 8/3 is 5/3, and you're done. So no complicated quotient rule, division rule necessary if you just do a little bit of simplification ahead of time. All right, well, I have more and more and more examples. There's an unlimited number of examples for these problems. There's one more here, J, which I'll demonstrate for you. And then we'll finish off the lecture today, the video today, with the idea of the second derivative. All right, so for this letter J, I have e to the x times x cubed minus x squared plus x minus 1. And so we're going to differentiate this one right here. So there is a parentheses, and so you could be thinking, hey, maybe I could multiply this out, right? Maybe I could avoid the multiplication rule, but just by distributing. If I distribute this, I get e to the x times x cubed. Those have different bases, so they cannot be combined together. I get e to the x times x squared, e to the x times x, and e to the x. And now I am just adding or subtracting different functions together. Unfortunately, each one that I'm adding together is a product rule. So I have to do the product rule for these two, the product rule for these two, the product rule for these two. This one's actually not hard to do. Derivative of e to the x is just e to the x. But I've made the problem actually more complicated by multiplying things out. That's my opinion, but I'm sticking to it. So not every time algebraic simplification is going to be helpful. In this case, I actually think it's a little counterproductive. So I am going to not multiply this out because it just doesn't get me anywhere. And instead, I'm just going to use the product rule to find the derivative. And I'll demonstrate once again the find the product rule. Oops. Let me get a better pen than that highlighter. So to find the derivative, you use the product rule. So it's the derivative of the first thing, which is e to the x, times the second thing, which is this big parentheses, and then plus the derivative of the second thing, which is the parentheses. Move me again over here, perhaps. And let me make this just a little bit wider. All right, there, I'm good. So the derivative of the second function, which is x cubed minus x squared plus x minus 1, times the first function. So derivative of the first times the second plus derivative of the second times the first. So now we can actually go ahead and do the derivatives. The derivative of e to the x is just e to the x. And then I'm going to multiply by the second thing. No derivative here, just the second thing. And then I do the derivative of this parentheses. The derivative of the parentheses is 3x squared minus 2x plus 1 minus 0. I won't write the minus 0 times e to the x. And so that's your derivative using the product rule. Again, if you want to simplify it, you could take an e to the x as a common thing. And you would get some stuff in the middle, which, you could combine things together. I'm not going to go through that because this video is going to be long enough as it is. But, these things can be simplified if you want to try that. So here's an example where I wanted to give this example where you might be tempted to do algebra because, you're kind of getting used to the idea that algebra simplification can be very helpful, but it's not helpful in 100% of the cases. So there's that little example for you there. All right, we're going to end this video with the second derivative. So you are going to be asked on occasion to find the second derivative, which has this funky little expression with squares, one of them in the middle between the d and the x, and one of them after the x. Oops, this should be just d squared y on the top. Typo, sorry. D squared y on the top and dx squared on the bottom. Regardless of why the intention for that particular notation for that way of writing it, let's go ahead and do the mechanics of how to find the second derivative. So the second derivative is just the derivative of the derivative. So we first have to find the derivative. So for this guy, I'm going to differentiate this. This is a sum rule. 4 times 10 is 40. I get one smaller exponent. 2x to the 1 plus 2. And then minus 0, which I don't have to write the minus 0 because it doesn't do anything. 2 minus 0 is still 2. So the derivative of the derivative is called the second derivative. So if I take the derivative of this thing, the derivative of the derivative, right, we get the second derivative. So that's the verb, take the derivative of this derivative function. And that's written, you may see, maybe start to see why, because we have two d's. So it's written as d squared y over dx squared. And then I literally just use the same shortcut rules on the derivative function. So the derivative of 40x cubed would be 40 times 3x squared. We could absorb the 40 and the 3 together, right? So people are used to that now. 40 times 3 is 120. The derivative of minus 2x is just minus 2, and the derivative of positive 2 is 0. So this is the second derivative of this original function. All right, so good time to pause and try them if you want. I'm going to do these last two solutions between you're trying them and me showing them. So go ahead and pause and see if you can find the second derivative of example L and example M. Okay, well, welcome back. I've written out my solutions for examples L and M. So for L, again, write the square root as x to the 1/2. And then I differentiate it, getting a one smaller exponent, which is now negative 1/2, making sure to multiply the constants together in front. And then I just differentiate again, getting one smaller exponent again, and once again multiplying the coefficient times that power that we wrote in front of the multiplication. So 6 times negative 1/2 is negative 3, and then x to the one smaller exponent, negative 1/2 minus 1 is negative 3/2. In the last example, we have a function right here, e to the x plus x. So I differentiate the first time. The derivative of e to the x is still e to the x. The derivative of x is 1. So that's the first derivative. And then I just differentiate again. The derivative of e to the x is once again e to the x. And the derivative of plus 1 is just 0. So I'm left with the derivative, second derivative, excuse me, equaling e to the x. Just e to the x just keeps coming back when you try to differentiate it. So it shed the x altogether, and the derivative, the second derivative of this original function is just e to the x. All right, well, that concludes today's video. Today, I tried to show you how to use the product rule and the quotient rule, the multiplication and division rules for differentiating more complicated functions. We also practiced using the 3.1 derivative shortcut rules, and also did a couple of examples of finding the second derivative. And lastly, if you remember to simplify things, you can oftentimes save yourself a lot of headache and a lot of steps. So simplification is one of the keys to doing complicated derivative problems without so much stress. Well, good luck on these problems in 3.2. As always, just reach out if there's anything I can help you with, if you want to see different examples. If you have some what if scenarios, like what would I do with this type of function? What shortcut would I use? Those would be fantastic types of things to forward to me so I can help you explore like what to do in different situations and more sort of nuanced cases that you may think of. We can explore the logic and what formula we use to help us find the derivative. All right, well, enjoy, and please let me know how I can help.